is to give you some practice on finding equivalent resistance for overall circuits. All right, so we're going to look at resistor combinations that are sometimes in series, sometimes in parallel, sometimes neither. They don't have to be one of those two categories. And we're trying to come up with an overall equivalent resistance that lets us simplify circuits for analysis later on. Okay, but before we get started, I wanted to talk about resistors in parallel when we have exactly two resistors in parallel. It turns out there's another calculation that you can use that I think is sometimes easier to plug into your calculator. All right, so I wanted to talk about that first. All right, so what we know is, and what we talked about on another video, is that the equivalent resistance of two things in parallel, hopefully you see these two are in parallel, that equivalent resistance is 1 over R1 plus 1 over R2. All right, so if I do a little bit of algebra and multiply top and bottom by R1, R2, then what do I get? Well, I get R1, R2 on the top. And on the bottom, when I distribute this across, the R1 cancels on the first term, and I'm left with just R2. And the R2 cancels on the second term, and I'm left with just R1. All right, so it's a quick way of calculating equivalent resistance for two at a time. There's not a corresponding formula for 3 at a time or 4 at a time, just looking at 2 at a time. But normally that's what we run across, is doing things 2 at a time. All right, so you take the product of the two resistors and you divide by the sum, and that's a quick way to put that into your calculator and get equivalent resistance. All right, so let's move on to some examples. All right, so in this example, I want to find RAB. All right, so here's some resistors connected with wires in a certain configuration. I want to find RAB. All right, so I could redraw this. Here's the equivalent circuit. See how much simpler this is. I want to find what's the value of RAB where I can make this equivalent circuit. All right, so my goal here is to try to look for things that are in series and try to look for things that are in parallel. Okay, remember my test for something being in series is, does the same current flow through both? Okay, and so these are my resistor values. I'm going to remove the highlights for now so that we can talk about different ones. I highlight these so you can tell which numbers go with which resistors, but I think it's pretty obvious in this case. All right, so I'm looking at this, and I got to start somewhere. So I'm looking for things that are either in series or in parallel. All right, and so my first choice that just jumps out at me is that I look at this particular current right here. All right, the same current flows through the 300 ohm resistor and the 200 ohm resistor. So that means these two are in series. All right, so let's highlight the things that are in series. All right, 200 and 300 are in series. All right, going back, the same current flows, right? This is a branch current, so it's the same current flows through the 100 and the 87.5 ohm resistor. So these two are also in series, and you can make the same argument about, if you reference current through this branch in this way, it's the same current flowing through both these, and so those would be also in series. Okay, so that's a good first step, and what we can do is you can start to simplify the circuit as you go. All right, so I'm going to get rid of this. All right, and I'm going to redraw this with some simplifications. All right, so here is this branch. I turned the 200 plus the 300 into a single resistor, and I add those together, so that'd be 500 ohms. All right, and then I take, the 15 I didn't do anything with. Nothing was highlighted there. So 15 ohms still. All right, and then I branch this way, and I have the 100 in series with the 87.5. So I can put that into an equivalent resistance of 187.5. Okay, I'm going to drop the ohms because it's crowds the diagram. Okay, and then the 75 and the 50 combine to 125. All right, so I leave everything else in the circuit. The 10 ohm is still there. This is connected. I make sure all the points are still connected. All right, so 200 and 300 is connected between this point and this point. All right, the equivalent is 500. It's connected between those 2 points in red. All right, so I just check that one by one. The 15 is connected between these 2 points in green, here and here, still connected. All right, and you get the idea. You check it. That looks like the equivalent circuit. This point is still A. This point is still B. All right. So now I'm looking at this, and I forgot to copy this 10 ohm down. Now I'm looking at this, and I see a parallel combination. Okay. You know, the 15 and the 10, they're not, they are in series, but you would have to rearrange these. So, yeah, that would work. You could look at this and you say the same current goes through the 15 and the 10, so you could move those to be in series and call that a 25 ohm resistor. All right, I didn't do that step. Let's just take it the way I see it next. The way I see it next is, here's a couple of things that are in parallel. All right, so these two resistors, let's make parallel be green. All right. These two are in parallel, and the way you see parallel is it the same voltage across each of the two? All right, I think parallel is a little harder to see. All right, so if you call that voltage V and you wrote a little KVL loop around here, all right, you'd get this voltage across the 125, that's a drop of V and then a rise of V, so V is equal to V. All right, that's one way of explaining it. All right, so it's the same voltage across them, so those are in parallel. All right, so I take my formula and I put 125 times 187.5 and divide by the sum. Okay, so when I do that, I get I get 75 ohms. Okay, so at this point I can replace the circuit again. I still have the 15. I now can replace that parallel combination with 75. So 15, 75, 10. Here's point B. Here's point A. 500 is still here. And 10. We've already marked that down. All right, so now I'm looking at this and I'm asking myself what's in series and what's in parallel. And so I can identify these three as having the same current going through them. So those are in series. Okay, so I can make that reduction. All right, and so that would be 100. And then on this branch, I have still the 500. And here's port B, or location B. All right, so now, it's a matter of how you draw it that makes it easier to see. I could redraw this and have it look like this. And I think that's a little more obvious that 100 is in parallel with 500. All right, so you can smooth out all the corners, you can shrink the wires, you can draw it however helps you see it. All right, but you have 100 in parallel with 500. So when I do that combination, 100 times 500 divided by 600, the sum, and I get the resistance being RAB is 83.3 ohms. Okay, so there's how you do that problem. Remember, we're working on the theory here. It turns out in practice, resistors aren't typically known to this level of precision that we're using. And sometimes we use something like a resistance of 1 or 3 or 5. Those aren't typical values. Normally with an electronics type of circuit, you see resistance like a 1 k ohm resistor. All right, so it depends on your application, but I just want to let you know that we're working problems to help us learn the theory, so sometimes we make up numbers that are just convenient to work with. That's largely what we're doing here. Okay, so there's one example. I wanted to calculate another example. All right, so RAB. All right, take a look at that. What would you see as a path through? So maybe pause the video and see what you would do. Okay, so I'm looking at this. I'm going to remove the highlights of the resistors. I'm looking at that, and what immediately jumps out to me is I see a couple of pairs of resistors that are in parallel. Okay, so do you see it? If I went parallel being green, this 2625 ohm resistor is in parallel with the 1050 ohm resistor. Okay, this 1800 ohm resistor is in parallel with the 900 ohm resistor. Okay, so I can immediately go and do those calculations. Okay, so 2625 times 1050 divided by the sum. Okay, that works out to be 750. That was no coincidence. I actually rigged the numbers to work out pretty cleanly. Normally when you do resistors in parallel, you get some decimal places. All right, but you get the idea. All right, next, 1800 is in parallel with 900, so 1800 times 900 divided by the sum. The sum is 2700. So that turns into an equivalent resistance of 600 ohms. And then on the bottom here, I have 200. All right. So next, I'm looking at this and I'm thinking, if I put current coming through this branch, all right, and maybe that's something that bothers you. I don't have anything connected here, so there wouldn't be any current. I just imagine if there were current, all right, what would it, would it be the same current? All right, and so if I applied a little voltage source right here, current would flow, all right, and it would be the same current flowing through each of these elements. All right, so those elements, because it's the same current flowing through them, those elements are in series. All right, so I could look at RAB in this case, and it's going to be the 400 plus the 750 plus the 600. It's not written very well. That's 600 ohms plus the 200. Okay, so I add all those together. I get 1950 for the equivalent resistance. All right, so I can replace this complicated circuit with an easier circuit, and those would serve equivalent purposes as seen by the battery that was trying to drive that load. It would take the same amount of current to drive that load with a given battery. Okay, so those are a couple of examples. You need to practice those. Again, my experience is that it takes a while for some people to see it, especially the parallel combinations. But then once you kind of have it click, it becomes fairly obvious how to do equivalent resistance.